What if we could find the sum of an infinite sequence of numbers? Let's consider the sequence generated by the explicit rule right here. I can tell from that explicit rule that this is saying that my first term is 1/2. Also, my common ratio would be 1/2. So imagine the sequence of numbers generated by that explicit rule. My first term would be 1/2, and I would multiply by 1/2 to come up with the next term of 1/4, and then 1/8, 1/16, and continuing on infinitely. Now imagine I take all of the terms of that infinite geometric sequence and I add them together. I can add them together and actually come up with a number. Imagine this as a pizza. I take one whole pizza. I cut it in half. Then I add another fourth of the pizza, and an eighth, and a 16th, and a 32nd, and a 64th. I could keep sectioning this one pizza up into an infinite number of slices by cutting the next slice to be exactly half of the width of the previous slice. But this is still just going to total one full pizza. The sum of this infinite sequence of numbers here would be 1. And not approaching 1, it would be exactly 1. Let's take a look and see how that plays out with the formula that we used on the previous page. Pretend I could say, let's find the sum of an infinite number of terms in a geometric sequence, where I'd start with my first term, which in this case was 1/2, and I do 1 minus 1/2 to the infinity power. Now I know that's kind of weird to write, but just go on this journey with me. And then 1 minus my 1/2. We've seen through our work with exponential equations in the past that when I take 1/2 to a really large power, that approaches 0. So if we think about simplifying this formula now, it would be 1/2 my original term, 1 minus, 0, and 1 minus 1/2. So 1/2 over 1/2 gets me 1. How is this possible? As we look at our sequence of numbers, the sequence 1/2, 1/4, 1/8, 1/6, 1/32, that sequence of numbers is approaching, like each term is getting smaller and smaller and smaller, but not smaller approaching negative infinity, smaller and smaller and smaller approaching 0. So I'm going to be adding these minuscule amounts that all are part of a total. In this case, as with the visual next door, that total was 1. Mathematicians have summarized it the following way. Given an infinite geometric series where our common ratio is less than 1, and in fact, they say the absolute value of it is less than 1, the sum of all the terms of the series is given by S equals A sub 1 over 1 minus R. Compared to the formula on the previous page, you'll notice that the expression 1 minus R to the nth power has just been, disappeared. How? Because it was virtually 1. So take a look at the sequence down at the bottom. I can see that they want us to evaluate the infinite sum here. I can see based on this explicit rule that I have a geometric expression. If I look at my common ratio, the common ratio is negative 1/3. That tells me that this sum will exist. If that common ratio was not the absolute value of it, not less than 1, that means that my terms would be continuing to grow from one to the next. So as I add the next term and the next term after that, the sum will continue to grow. Using this new formula, we can identify a sub 1 as 5. We can identify our common ratio as negative 1/3. I want you to think, if you were only given this representation, could you have picked out this information of your first term being 5 and your common ratio being negative 1/3? What if instead of that representation, what if you were given this instead? And they said, find the sum. Would you have been able to tell that the infinite sum would be defined? Could you identify the first term and that common ratio? If I have these pieces of information, then I can find my infinite sum as the first term, 5, 1 minus my common ratio of negative 1/3. Working through the arithmetic, I get minus a negative, which tells me to add, and I get 4/3 for my denominator. And I know that dividing by 4/3 is the same thing as multiplying by 3/4, and I will get 15/4, or 3.75. Believe it or not, you can check your answer using summation notation in your technology. The problem is you can't write an upper bound of infinity, so pick a really large number. Suppose you said you wanted to add from your first term to the 10,000th term or the 1,000th term. You should get a value of approximately 3.75, but a lot of times it will show up as that sum, 3.75 exactly. Try this one. Notice the directions say find the sum if possible. So don't rush off to use your formula. First, you have to determine, would this infinite sum be defined? If so, then calculate.